Hello everyone, today I will introduce the modern portfolio theorem. Let's turn to the page 2. The modern portfolio theorem was introduced by Henry Markowitz in 1952 and is the important theorem in finance. MPT provides a thematic method for portfolio management aiming to achieve an optimal balance between the risk and the return. And next, we will introduce some core concepts. Let's turn to the page 3. In MPT, a portfolio can be characterized by its expected return and the risk. The goal is to find portfolios that maximize the expected return for a given risk or minimize the risk or given a return. These optimal portfolios forms what is known as the efficiency frontier. We will introduce it in later. Let's turn to the page 4. There are some key concepts. The first, efficient frontier, represents the site of the all mean variance optimal portfolios. Portfolios on the efficiency frontier achieve the best trade-off between return and risk. Investors can choose different points on the frontier based on their risk performance. When a risk-free asset, such as the government bonds, is introduced in the efficiency frontier, expands to a new boundary. By comparing a risk-free asset with a market portfolio, it's possible to further enhance the risk-return efficiency. This resulting line is known as the capital market line, which represents the optimal risk-return combination between that can achieve a balanced market. Built on the foundation of the MPT, the capital asset pricing model (CAPM) links to the return, risk, and the market equilibrium. CAPM further explains the thematic and unthematic risk. According to the CAPM, the return of an individual asset can be explained by its sensitivity to overall market risk. For example, it's the beta parameter. Let's turn to the page 5. There are some assumptions for the MPT. The first, investors seek to maximize the expected return of the total wealth. And secondly, all investors have the same expected single period investment horizon. All investors are risk averse. That is, they will only accept the greater risk if they have the higher expected return. And firstly, the investors base on their investment decisions on the expected return and the risk. The last assumption, all markets are perfectly efficient. There are 5 assumptions for the MPT. Based on these assumptions, we will do our programs. Let's turn to the page 6. Suppose there are n assets in the portfolio, and the mu I denotes the expected return of the asset I, and the Wi is its weight. The expected return of the whole portfolio is equal to the weight times the expected return and the sum of all the assets until the n. And the variance portfolio sigma p square follow the same construction. And when we know the expected return of the whole portfolio and the variance of the portfolio so we can turn to the page 7. The investor opportunity side is the side of the portfolio expected return mu p and the standard deviation sigma p for all possible portfolios with the weight summing to 1. Firstly, we introduce the efficiency frontier. Let's turn to the page 8. The efficient frontier represents the size of the opportunity portfolios that provide the highest expected return for a given level of the risk. Each point represents the potential portfolio. Portfolios on the upper left part of the curve are considered efficient, as they maximize the return for a given of the risk. Let's turn to the page 9. This is our optimization progress. Based on the investor's performance, the mean variance model can be divided into two cases. The first, minimize the risk for a given expected return. Subject to the expected return of the portfolio equal to the mu P0. And moreover, the other constraint is the sum of the weighting need to equal 1. And the other case is that the maximized expected return for a given of the risk. And subject to the covariance equal to the specific level, such as the sigma P0 square. And the other constraint is the same, sum of the weighting equal to 1. To get the optimal weight, we need to use the Lagrange function to solve these problems. Let's turn to the page 10. We use the Lagrange function to solve the problem of the minimized risk for a given of the expected return mu P0. We use the multiply lambda 1 and lambda 2. So we can get the first order conditions to derivative with the x, lambda 1, and lambda 2. We can get the equation 1, 2, 3. So from the three equations, we can get the final result. Let's turn to the page 11. The FOC can rewrite in the matrix form. And so in this form, we can solve the optimal weight easily. We denote the first matrix is A, and ZX what we want, and the B0 we also know. So the optimal weight ZX equal to the A inverse times the B0 if the matrix A invertible. Let's turn to the page 12. There are some other solutions to solve the optimization problems. From the equation 1, we can get the x optimal x expression, and moreover, we can define the matrix M, which combined with the vector mu and the vector of the 1, and the vector lambda combined with the two parameters lambda 1 and lambda 2. So we can rewrite the x like this expression. We need to find the value of the lambda 1 and the lambda 2. We can use the equation 2. We pre-multiply the equation 4 and by the mu transpose and use the equation 2. So we can get the expression for like the equation 5. Moreover, similarly pre-multiply the equation 4 by the 1 transpose and use the equation 3 condition to get the equation 6 result. Next, we turn to the page 13. We have the two linear equations 5 and 6 involving the lambda 1 and the lambda 2, which we can write in the matrix notation. And we define the middle matrix equal to the B, and mu P0 and the vector 1, we define the mu P0 tilde. So we can rewrite the lambda equal to the equation 7. And when we get the parameter lambda, we can substitute lambda back into the equation for x to give the expression for the efficient portfolio with vector x. So we get the final result for the optimal weight for the optimization problems. Okay, let's turn to the page 14. This is the dual problems. We maximize the expected return for given the risk. we will skip the step-by-step to prove what's the optimal weight because it's the same method. So we can also use the Lagrange function and the derivative to the x1, lambda 1, and lambda 2. So next we will focus on the tangency portfolio. Let's turn to the page 15. The tangency portfolio is the portfolio of the risky asset that has the highest Sharpe ratio. The tangency portfolio solves the constraint maximization problem like this term. The maximize the Sharpe ratio. The Sharpe ratio equal to the return minus the risk-free rate divided by the sigma, the risk divided by risk, such that the sum of the weighting equal to 1. And moreover, you also use the Lagrange function to solve this problem, and we use the parameter lambda, and to using the chain rule, the first order condition, we can get the this expression, and moreover, we can get the final result. Let's turn to the page 16. We can get the nice simple expression x, and we can compare with the x and we can compare with the mu PM and the risk-free rate. What is the mu PM? Mu PM is the global minimal variance portfolios. So if the mu PM larger than the risk-free rate, then the tangency portfolio always have the positive Sharpe ratio. However, if less than the risk-free rate, the tangency portfolio will have a negative Sharpe ratio. So we can, for simply, we can see the picture. Let's turn to the page 17. So we can see that this picture expresses the efficiency frontier with the tangency portfolio and the capital market line. So the red star denotes the tangency portfolio, the portfolio of the risk assets that maximize the Sharpe ratio. The orange dashed line represents the capital market line, which combines the risk-free asset with the tangency portfolio to form the optimal portfolios. Okay, let's turn to the page 18. From our previous discussion, we focus on the objective of the maximize return for a given of the level of the risk, or minimize the risk for a given level of the return. This approach leads to construction of the efficient frontier, where each point represents an optimal portfolio for a specific risk level. The goal was to identify portfolios that provide the highest possible return for a specific risk without considering individual risk performers. And we need to consider utility function while transition to utility function. The efficient frontier does not account for investor-specific risk tolerance. To personalize the portfolio choice, we introduced a utility function that reflects the trade-off between the expected return and the risk, adjusted by the investor's level of the risk aversion. That's our reason why we need to focus on the utility function. So let's turn to the page 19. This is our utility function equal to the expected return minus gamma divided 2 times the volatility. So we want to maximize this utility function. And because there are no constraints, so we derivative for the utility function with respect to the x. So then we can get the optimal weight for the x star. And we can see if lambda is larger, the investors is more risk averse, leading to a low proportion of the risk asset. However, if lambda is small, the investor is less risk averse, leading to a high proportion of the risky asset. Let's turn to the page 20. The first optimization problem, we consider no constraints for the utility function. In this way, we will adding one constraint is the sum of the weighting equal to the 1. So, to solve this optimization problem, we will introduce the Lagrange function lambda to solve this problem. We introduce a Lagrange multiplier lambda and construct the Lagrange function. So, and then we can derivative for the x and the lambda. So we can get the first order conditions like the equation 13 and 14. From the equation of the 13, we can get the x expression, but there is the one parameter we don't know, that is the lambda. So we need to use the equation 14 to get the lambda expression. Let's turn to page 21. Next, to find the value for lambda, promoting equation 15 by the one transpose. So we can get the lambda expression like the equation 17. Moreover, we can substituting lambda back into the expression for x. We can get the optimal portfolio weight. That's our final result. So we can turn to the page 22. Comparing with the traditional investing and the ESG investing, because the ESG is more and more popular, adding ESG is become an important. Adding an ESG dimension to consider environmental, social, and governance factor in the portfolio optimization process. We can divide the three types of the investors. First is type U, ESG unaware investors. That's the people who are unaware of the ESG score. And the other type is the type A. The ESG aware investors have the mean variance performance, but they use the asset ESG score to update their views on the risk and expected return. Type M means the ESG motivated investors. They use the ESG information and also have the performance for the high ESG score. Let's turn to the page 23. This is the ESG Sharpe ratio efficient frontier. And later we will introduce how to plot this efficient frontier. And this frontier extends the traditional mean variance framework by incorporating ESG score. Shows the highest achievable Sharpe ratio at the different level of the ESG investment. Demonstrates the trade-off between the risk, return, and the ESG performance. Let's turn to the page 24. This is our objective function. The utility equal to the expected return minus volatility and add to the performance function. This F represents the ESG performance function. And the X bar means the weight of the sum of the ESG score. And we want to solve this maximized problem. And firstly, we rewrite this problem. The utility maximization problem can rewrite as this expression. We given the X bar and the sigma. And then we solve this optimization problem only depends on the variable x. So let's turn to the page 25. The investor problem can be viewed as, firstly, we choosing the best portfolio at a given level of the sigma and the X bar. And then we maximize over the sigma and the X bar. So under this way, we can solve this problem. The former problem is solved by choosing the portfolio with the highest Sharpe ratio for given level of the ESG score. So as the result is like this way, and this Sharpe ratio means the highest Sharpe ratio given the X bar. And the first, this expression, the first can be divided into two components. The first component is the ESG Sharpe ratio frontier, depends only on the securities. And the second term, we can denote the performance term. It depends only on the investor's performance. Let's turn to the page 26. Before solving this problem, we can get the expression for the Sharpe ratio given the X bar. So we can get this term, and moreover, it's simply to get what is the maximized Sharpe ratio. It's equal to the square of the mu times the sigma inverse and times the mu, and one which is attempted with the ESG score, the X star equal to the CS mu divided by C1 mu. This is our whole presentation. Thank you for your listening.